All right. Next up in our list of examples is going to be the capacitance you get when you have a cylindrical capacitor. So the picture that I have in mind is the following. Imagine that we had a cylinder, maybe one piece of metal, it could be a wire, or it could be a cylinder. And we can go ahead and say that has a radius, let's say this has a radius Ri for R inner. And then there's another cylinder with a larger radius, call it RO for R outer. So this is like a coax cable. You know, the old-fashioned cables that you would use for your television set would have a wire down the center, and then there was a cylinder, a cylindrical wire that would which surrounded it. It's a coax cable. So we would be calculating the capacitance in a coax cable, if you want. So if you think about it, that cable, that coax cable, could be really long. You might say almost infinitely long. So if we do that, we can use Gauss's law to do the calculations for the electric field. And then it's really very similar in spirit to the parallel plate capacitor example, where we use Gauss's law to get the electric field, and we integrate the electric field to find the change in potential, and then from that we deduce the capacitance. In this example, I will make the core have negative charge. So we'll say that has minus, let's see, how do I want to say that? Let's say that that has, let me choose you know what, I'm just going to say it has a charge of minus Q, and I'm just going to say that the outer edge has charge plus Q. All right, and that we're going to assume that in the gap in between, in this region right here, there's no charge. So if there's no charge here, then, well, that's what we're going to do. Okay. And we're going to take the cable to be really long, you know, give it some length, total length, L. So, you know, just a huge number that is just not going to matter. And, okay. All right. So we can do that. Now, the first thing we have to do is to determine we're going to determine the electric field in that long cable. So what I'm going to do is I'm going to imagine wrapping the center cable with or center wire with a Gaussian surface that runs the length of the cylinder. And I use a cylindrical Gaussian surface because the distribution of charges is cylindrical in character 2, and the Gaussian surface always inherits the symmetry of the charges. Okay, so now we proceed. You know what? I'm going to cheat. I'm going to make this thing positive. Sorry, positive on the inside. I'll say that I have a negative charge on the outside. All right. So now let's find a formula for the electric field. So to do that, I want to calculate the flux. So the electric field is going to, sorry, the flux is going to be, so Gauss's law says the electric flux is Q enclosed over epsilon naught. Well, Q enclosed, the way I drew it, is actually the total charge. So that's just Q over epsilon naught. And then the flux is going to be because the flux is outward bound only, the caps won't matter, or they will make a negligible contribution. So that's fine. And then the electric field, by symmetry, cannot depend upon the angles. It can only flow outwards, which means that as you go around the surface, the electric field is a constant. So you can write that as the electric field times the area of the walls of kind of the tin can, the soda pop, or soda can. So that's going to be 2 pi r, and it should be little r, because that's where the Gaussian surface is evaluated. 2 pi little r times the height of the can, the tin can, which is an L. So that's going to be 2 pi little r times L. And the electric field we find in the gap equals the total charge over 2 pi little r L times epsilon naught. All right, so that is the formula for the electric field in the gap between the inner wire and the outer kind of cylinder of wire. Good? Now, remember, keep your eye on the prize. We're trying to find the capacitance. So to find the capacitance, we don't want E, we want delta V. So to find delta V, and we want to write it as a positive quantity, so we want to start on the negative charge and integrate towards the positive charge. So that means we want to start at R outer and integrate to R inner. So let's do that. Delta V, the positive part, across this capacitor is going to be the integral, minus the integral from R outer to R inner. And I should integrate the electric field in the gap dotted with dr vector. Now, in this case, we're integrating along a straight line from R outer to R inner. It's a straight line along the radial direction, which means dr vector is just dr coordinate times r hat. And so the dot product becomes trivial, and this becomes minus the integral from R outer to R inner. The electric field we just found, Q over 2 pi L epsilon naught, 1 over R, 2 pi L epsilon naught over R times dr. So I want to, before I do anything further, let me highlight something that happened both with the parallel plate capacitor and now with this example. And it's a fact or a feature or a property of these calculations that throws people off. When you do the flux integral, that was over the Gaussian surface. That went around. When you do the delta V calculation, that's over the radial direction. And that's always how it works. The flux calculation is over the curve where the electric field doesn't change. The voltage, or the electric potential calculation is over the direction where the electric field does change. So the flux integral is over a surface perpendicular to the potential integral. So in the end, you're integrating over everything, but you adjust the integrand. But you have to keep track of whether you should be integrating over a surface, like when doing the flux, or the line integral over the perpendicular direction when finding delta V. Basically, if you can't think it through, that's okay. There are only a finite number of examples. Just work each of them to death. and then you can almost just memorize your way through it. They're only in about 5 cases. But anyway, it's tricky to keep track of when you integrate over the surface versus when you integrate over the perpendicular directions. The surface is for Gauss's law, and then the potential integral is going to be over the perpendicular direction. Excuse me. Okay. Oh, very good. And we can do this integral now. So let's do that. I can write this as delta V equals, I'm going to pull all these constants out. I get minus Q over 2 pi L epsilon naught integral of 1 over R from R outer to R inner dr, which simply gives me minus Q over 2 pi L epsilon naught. This gives me log of R inner over R outer. But because R inner is smaller than R outer, that logarithm will be will be negative. But I have a minus sign out front. So what I can actually do is bring that in here and using, remember the law of logs? First law of logs? Don't drop them on your feet. No, the minus sign out front on a logarithm actually just takes the reciprocal of the argument. So that becomes R outer divided by R inner. And that's the correct answer for the difference in potential between the inside and outside of a cylindrical capacitor. Now, that's the potential. I really want the capacitance. So that the capacitance is Q divided by V, which means I should have Q divided by V. So I learned that the capacitance for a cylindrical capacitor equals 2 pi L times the log of R, not times the log, divided by the log of R outer divided by R inner, and I have to multiply by epsilon naught. Okay, as advertised, again, this prefactor is all geometry. L, 2 pi because it was round, radii. The epsilon naught is there as well. So geometry times epsilon naught. The other thing I wanted to emphasize is that it has a kind of funny thing where if you were to try to make the inner radius go to 0, make it skinny, look what happens. This ratio gets large, and the logarithm of a large number, well, logarithms grow monotonically as well. So, I mean, if you really took this inner radius to go to 0, it would blow up logarithmically. Of course, when you make a real device, what you could have is a very skinny wire with a large walled capacitor, and that would give you a large capacitance, which would mean that you could store a lot of charge per volt on this device. Okay, stop there.